let me tell you about a puzzle that fooled Einstein himself. When you look at a black hole mathematically, something terrifying seems to happen at the event horizon. The equations appear to blow up and time itself seems to stop. Einstein looked at this and concluded that nothing could ever actually cross the event horizon. But here's the beautiful thing. He was wrong. Let me show you exactly what fooled him. In these coordinates, there's something called a metric, which tells us how time flows and how distances work in curved spacetime. It has two key pieces. One controls time and one controls space. Watch what happens as we approach the event horizon. The timepiece shrinks towards zero, which means clocks slow down, while the space piece grows toward infinity, stretching distances out. A clock near the horizon ticks slower and slower, distances stretch toward infinity, and it looks like space-time itself is breaking apart. But here's where we have to be clever, because just because the numbers in our equation blow up doesn't mean the physics is blowing up. We have to ask ourselves, is this a real physical infinity, or is it just our coordinate system misbehaving? Think about it this way. When I describe a point on Earth using latitude and longitude, what happens at the North Pole? At the North Pole, all the longitude lines converge to a single point, and if you try to define longitude there, you'd get nonsense because every direction is south. But does that mean there's something wrong with the North Pole? Of course not. The ice and snow there are perfectly ordinary, and you can walk right across it. The problem isn't the pole itself. The problem is that latitude and longitude coordinates break down there, even though the actual surface of the Earth is completely smooth. So how do we test if space-time itself is singular, or if it's just our coordinates playing tricks on us? We compute something called the Kretschmann scalar, which is a coordinate-independent measure of curvature. K equals 48 g squared m squared divided by r to the sixth. At the event horizon, when you plug in r equals 2gm over c squared, you get a perfectly finite number. The curvature is finite, which means space-time there's actually smooth. This has a profound physical consequence, so let me show you two very different perspectives. On the left, we see what the falling astronaut actually experiences, which is called proper time. Their clock counts normally, and they cross the event horizon in about 10 microseconds for a solar mass black hole. On the right, we see what a distant observer watching from far away would calculate, using coordinate time. To them, the astronaut appears to slow down and freeze at the horizon forever. But here's the key insight. The astronaut feels nothing special when they cross. No infinite forces, because space-time there is actually smooth. Now, there is a place where physics genuinely breaks down, and that's at r equals 0, the very center of the black hole. If you look at the curvature scalar again, you'll see that as r approaches 0, it shoots up to infinity. The curvature really does become infinite there. Tidal forces would stretch any object into an infinitely thin strand, and this is the true singularity, not the horizon, but the center, where physics as we know it comes to an end. So here's what we've learned today. The event horizon, that outer boundary, is where our coordinates break down, but space-time there is perfectly smooth, and an observer can cross it without feeling anything unusual. The true singularity is at the very center, at r equals 0, and that's where curvature becomes infinite. What really happens there remains one of the deepest mysteries in all of physics. For more science and technology videos, please subscribe to our channel. Thank you for watching, and I'll see you next time.